Welcome back. This will be lecture 17 of EC253C, course on microprocessors and microcontrollers. We have been discussing Atmega 328 microcontroller, and in last lecture we discussed a program to blink LEDs that were connected to port B of Atmega 328 and incorporates some delay between the blinks between every on and off cycle. In fact, after every on, the LED should be on for some time. There should be a delay before turning them off, and when the LEDs are off, there again should be some delay. So previously we have done it without using a subroutine, and then we discussed it how to use a subroutine, how to call a subroutine. So we discussed various call instructions like call, a call, I call, and then call, R call, and I call, E and EI call. So this is the program in which we blink LEDs connected to port B. We have already discussed this in the last class. First of all we will be using these two instructions. We are configuring the port B as output. Then I am temporarily loading some data into these two registers R17 and R18 here, and in this instruction whatever is in R17, that is FF, I am sending that to port B and effectively turning LEDs on. And then I am calling a subroutine that I have named delay. I could have named it anything, that I have named delay, and this actually incorporates the delay in our program, this subroutine. And then I am sending the data of R18, that is 00 to port B, effectively turning the LEDs off, because in R18 I have 00, again some delay, and then I'm repeating the cycle using the jump instruction. So next I have to actually define delay function. So delay function is simple. I'm loading any of the general purpose registers with some value, in this case the maximum value FF 255, and then I think I have missed one instruction, decrement, here. So it will be something like this. We must have decrement first. I have loaded R20 with some value. Now I am decrementing R20, and then I am checking whether R20 has reached 0 or not. If it has not reached 0, it will again jump to XYZ, no operation, and then decrement it again, decrement the R20 again, and then again check until it reaches 0. Once it reaches 0, the next instruction will be executed, and that instruction is RET, return. That means return to the main program. That means return to the instruction exactly after the where from the delay was called. So if delay was called here, the control will be returned to this instruction, and the LEDs will be turned off. Then delay will be called again, and after returning from the delay subroutine, the control will be transferred here, and the cycle will repeat. It's as simple. So now the first question that arises, I have given the address locations where finally the opcodes of these instructions will be burned. Since most of these instructions are 1 byte instruction, except call, that is a 4 byte instruction. Most of these instructions are 2 byte instruction, 1 word instruction. But call and jumps, they are 2 byte instructions. So our program, the opcodes of these instructions, of every instruction, will be stored something like this. The first instruction at 0000, you should remember that these addresses point to the words, that means 2 bytes. So the first instruction will be stored at memory location 0000, next at 1, 2, and then at 3, then at 5. Then the next call will be saved at memory location 5 and 6, then 7, then 8 and 9, this call, the next call. And then the last instruction, that is jump, that will be saved at A and B memory location. So the first question is, where will be these instructions, the instruction of the subroutine, saved? Will they be saved from memory location C or some other memory location inside the ROM? Why will the first, in fact, then why will be, the question is exactly why will be this first instruction saved? The next instruction will be saved in a sequential order. So why will be the first instruction of any subroutine saved? So let's get back to few lectures when we discussed why will be this instruction saved. The first instruction, I said the first instruction will be saved at 00000, and it should be saved at memory location 0000, because when the microcontroller at mega 328 wakes up, that is, it's powered on, the first instruction, it expects it at memory location 0, because the program counter initially has the value 0. So it expects the first instruction at memory location 0. So how we inform, or how we direct our compiler to put the first memory location, first instruction, the opcode of first instruction at memory location 0? What we do, we use an assembler directive, that's a pseudo instruction. We direct this assembler why to store the first instruction, that is org. I have discussed it earlier. That means I will write dot org 0h. In fact, this will be my first statement in every program. That is, in every program from now onwards, you should remember that every program will start with .org statement, so that it will direct the compiler that the first instruction should be stored at memory location 0000, because that is what our microcontroller expects, that the first opcode, the opcode of the first instruction should be saved at memory location 0000h. And how do I do that? How do I direct the assembler to store the first instruction at memory location 0? I write this assembler directive .org 0h, so you should remember that this should be the first statement of every program, every microcontroller program, every program related for Atmega microcontrollers. The first instruction should be .org, and preferably 0h. In fact, it is necessary to write 0h because our microcontroller expects that the first instruction will be at memory location 0h. And what after that? So, and the next instruction, this instruction, then this, all these will be in the sequential order, because program counter increments itself after execution of the instruction. It always points to the next instruction to be executed. And in case of jumps or calls, program counter is fed by the processor some other value depending on how we are calling or how we are jumping. So now coming back to this question, why will be the first instruction of this of the subroutine saved? For that, we need to write one more org statement here before the start of the subroutine. Before the first instruction subroutine, we need to write one more org statement. That means we will direct our compiler why to store this subroutine. It can be stored anywhere inside the program, inside the ROM of AVR microcontroller, but we will direct it why to store. And what are our constraints? The only constraint is that it should be stored somewhere after the program ends. The program in this case ends at memory location B. So we can store it anywhere. I can store it from memory location C. I can also store it from memory location 10. I can also store it from memory location 1F. I can also store it from memory location 200. Maybe, for example, keeping some space in between, and that is not necessary. But sometimes maybe we have miscalculated the total amount of memory our main program is taking. This time I have calculated it is a very small program, and I have calculated that this program will take memory location from 0 to B. So I can place my subroutine anywhere after B. But sometimes when the program is long, we don't exactly calculate the number of memory location our program is taking, but we take a random guess, and then put our subroutine after some particular memory location. For example, I will write .org 100h 100, because my guess is that my program only consists of maybe 9 or 10 instructions, and they will fit in 9 or 10 memory locations, maybe 12. So I am putting my subroutine at .org 100h. So what will happen when I will compile the program? The first instruction that the compiler will encounter will be this 0 instruction. Of course, this is a 0 instruction and thus only a command for the compiler. So it won't change into opcode, but it will direct the compiler to store the opcode of the next instruction at memory location 0h. So it will store this. So compiler will store this instruction, the opcode of this instruction at memory location 0, and similar and so on. The opcode of this at 1, 2, similar until this instruction. And when after this instruction our compiler will encounter this 0 code .org 100h, so it will understand that the opcode of the next instruction needs to be stored at 100h. So it will store this instruction, that is the first instruction of the subroutine, at 100h, memory location 100, that means 0100. And the next instruction will be stored at 0101, the next instruction at 0102, the next instruction at 0103, and then the the last instruction in the subroutine. And the last instruction should always be RET, because it tells the compiler, or it tells the processor that the subroutine has finished, and now you should move back or transfer control back to the main program. So last instruction will be stored, because this is a 2-byte instruction, it will be stored at 103 and 104. So this will be stored at 105. I think that is fine. You have understood why the subroutine will be saved. I could have easily written some other number here. Maybe I could have written 200. So my instruction inside the opcodes of the instruction inside the subroutine will be saved from 200. I could have even written, for example, I could have even written a 10 here. ORG, not 10 because A has already been used. B, I could have written from CH. So this instruction will have been saved at memory location C, and then this at D, this at C, this at D, this at E, this at F, and F after F, what is 10? F and 10, and this would have been saved at 11. But I have written 100h here, so let's go with 100h. I think that is fine until now. So one more thing I want to discuss. Instead of this delay, again I told you that this delay or this ABC, even this ABC, these are optional, in the sense that I could have written the address here. For example, I could have written call, instead of this instruction I could have written call, CALL, and the first instruction of the subroutine, that is 100 in this case. So I could have written call 100h. In fact, when I write call delay, the compiler changed it to call 100h. And in case of jump ABC, I could have written maybe jump 0004. So that's also simple. You have understood this also. Instead of call, in fact here also I could have written call 100h. And this 100, it could have been anything where I have stored my subroutine. That means it could have been 200, 300, 2000, 3000, anything. So let me focus on this, writing address instead of the subroutine, instead of the label. When I write address instead of the label, for example, I write call 100h, that means this label also becomes optional. I could have written the label. In fact, I can write the label of any instruction. Any instruction, for example, this instruction I can also label as maybe AZY. I can label any instruction. It's not necessary to label only jumps. It is necessary to label those instructions where I have to jump or the starting instruction of the subroutines. But theoretically, I can label any instruction, but that won't serve any purpose. But since I am now changing it from call delay to call 100h here, so I can drop this label also. That's one thing. Now the other thing, what's the difference between call and relative call? Because last time I told you that the call, the way in which we call subroutines are 4 types. A simple call, what we call as long call, is a 4 byte instruction, and then R call, I call, and EI call. So let me discuss how I could have used R call here. For example, if the program was like this, that is, I have used label, I could have simply written, instead of call, I could have simply written R call. The rest of the things would have been same. So this program or call or simple call, it would have made no difference. The program execution will be similar, but where the difference will be? The difference will be in the storage of these opcodes. Since the first opcode was stored as 0000, 0001, 2, 3, 4. The opcode of R call delay is only 2 bytes, so it will be stored at memory location 5. And the next will be stored at 6, and then at 7, and this will be stored at 8. So effectively it saved my 2 bytes. Sometimes these bytes are very important. When we have long programs, we need to save as many bytes as we can. But what is the downside? For example, the downside is that this address now, this starting address, the starting address of my opcode, it cannot be anywhere in the program. In case of call, when I used call, it could have been anywhere inside the ROM. But in case of our call, it needs to be within 64 kilobytes of this address and this address. I hope you are getting my point. When I used call, I could have written this subroutine anywhere. That's I could have used this program. I could have used any number here. I could have started my subroutine anywhere inside ROM, because I had 2 bytes to put the address here. I had 2 bytes to put the address here, and using 2 bytes, I could have written. In fact, I have not 2 bytes, but I have 22 bits. Sorry, 22 bits. I have 22 bits, and I could have written this program. I could have written the subroutine anywhere. But when I use a call, I don't have that luxury. I have to write my program within 64 kilobytes of the memory location from where I am calling the subroutine, because OR call is only 2 byte instruction and only 12 bits are used for the address. 12 bits translate to, that means it can be either from -2048 up to 2047 memory locations. That means either it can be before 2048 memory, within 2048 memory location from either side from where I am calling this subroutine. So for example, now coming back, if I used an R call here, R call delay, and I am using the same address 100h, so what will happen? What if I change it that means I don't want to use this delay label, but I want to use this address. So what address I have to write here? Or call, what's the address that I have to write here? In the previous case, when I used call, I wrote the address directly 100 but this time, since a relative call, if you remember, I have told you that in case of relative call, the contents of program counter, when the call instruction is executed, are added to this address, and that address, the sum is fed into the program counter. That means the target address is calculated by adding the current contents of program counter with this number, whatever is written here. So since we have to jump as 100h, what is the present value of the program counter when this instruction is executed? What will be the value of program counter? If you remember, program counter always has the value of the next instruction that is executed. That means when our call here is executed, program counter will have a value of 6h. That means 6 or 6 in binary. That means I must have 94 in binary, not in hex here. So I can write, instead of writing or call delay, I can write or call 94. And what will happen? This 94, when this instruction will be executed, or call instruction, this number, the number 94, will be added to the program counter, that is value 6, and jump address or call address will be calculated, that is 100. That means our program will jump here. Similarly, in this case, since when this instruction will be executed, this or call program counter already has a value 8. That means instead of or call delay, I have to write or call. In place of delay, I can write or call 92. And this one and this same thing. Let's next discuss role of stack. What's the role of stack in microcontrollers? Particularly in calling subroutines. You should remember that to make sure that the microcontroller knows where to come back after execution of a subroutine called subroutine. Microcontroller has called a subroutine here, the control jumps here, and these instructions are executed, and whenever the return instruction is executed, the control has to get back to the main program. That means it has to get back here. That means it needs to save this address 006 or 007, whatever it is. It has to save it somewhere. So to make sure that the microcontroller knows where to come back after execution of the called subroutine, this microcontroller, during the execution, during the calling of the subroutine, it automatically saves on stack. While it saves on stack the address of the instruction immediately below the call. That means whenever the call is executed, this instruction is executed, the control is transferred here, the address of the next instruction, in this case the address of this instruction, and in this case the address of this instruction, will be stored automatically. And while it will be stored on stack. We have not yet discussed what stack is, but what we know, that stack is used to store the instruction, to store the address of the instruction immediately below the call, so that when a subroutine is called, control is transferred to that subroutine, and the processor saves the program counter of them. That means saving the address of the next instruction, saving the address of the instruction immediately below the call. What does that mean? It means that the processor actually saves the value of the program counter on the stack, and after that it begins to fetch instructions from the new location, that is from the subroutine. After finishing the execution of the subroutine, that means after executing all the instructions inside the subroutine, when the last instruction is executed, that is RET instruction is executed, what happens? This the execution of the RET instruction actually transfers control back to the main program, or to the program, to the subroutine where from this subroutine was called. So that means every subroutine needs RET as the last instruction. So what actually RET does, it takes out the address saved on the stack and puts it in program counter. For example, when this wait a second when this program was executed, we reached to this instruction. What happened? This When this instruction was executed, processor knew that I have to the next instruction that is to be executed is the first instruction of a subroutine. So the program counter automatically saved the address of this instruction, that is number 0006 000006 on stack. So stack has this number 0006. Stack is memory. Actually, it's part of RAM. We will be going to discuss that. This and when the control is transferred to subroutine, and these instructions are executed, and when the last instruction, that is RET, is executed, RET actually transfers control back to the from where this subroutine has been called. So when RET will be executed, in this case, what will actually happen? This number will be taken out from stack and put in program counter. That means program counter will have value 0006, so that this instruction will be executed next. And similar thing will happen when this call is encountered. So this is stack. Stack is a memory where it's actually a section of RAM, and it is more often used by CPU. Sometimes it can also be used by the programmer to store data temporarily, and this data, it can be either data or address. In case of when the CPU uses it automatically, more often than not it is the address, and the address and when it is used, mostly it is used when we call subroutines. Stack, it's a section of RAM, and it's used to store data temporarily. This data can be address, or this data can be simple data, and it is used either by CPU automatically, or it can also be used by the programmer. When the CPU uses it, the most common example is when we call subroutines. The CPU uses it to store the address of the instruction immediately below the call. That means to store the contents of the program counter. And when the last instruction, that's RET instruction of the subroutine, is encountered, this value is taken out of the stack and put into the program counter, so that the next instruction after the call will be executed. Okay, I think that's fine until now. So the next question is, how is stack accessed by the programmer? Since the stack, as I said, is a section of RAM, there must be a register inside the CPU to point to it, to actually have the address of the stack where I need to store the information. For that, we have a register that's used to access stack, and it is known as stack pointer. And in most of the AVR microcontrollers, this stack pointer is actually a 16-bit register consisting of two registers. We call them SPL and SPH, and both of these registers are 8 bits long. So there are two new concepts, stack and stack pointer. Stack, as I've said, is a section of the RAM, and stack pointer is the register which is used to point to the stack where we have stored the information. And what is stack used for? We have got one use of stack, that is it is used by the processor to store to actually store the address of the instruction immediately below the call. And this address is when the RET instruction, that is the last instruction of a subroutine is executed, this instruction is taken out of the stack and fed to the program counter. And then we have also discussed stack pointer, and I have told you in most of the microcontrollers, in most of the AVR microcontrollers, it's 16 bits wide, and we have two different registers, that means stack SPL and SPH, both are 8 bits wide, and they constitute stack pointer. What's the exact role of stack and stack pointer? I think we should discuss that in the next class. That's enough for now. Thank you.